The Boolean satisfiability problem lies at the heart of today's most complex computer science challenges, from static code analysis and constraint solving to software verification and security research. This problem is so commonly referenced that it's simply referred to as SAT. But before we dig into SAT and how it relates to SMT, let's cover some Boolean logic principles first. You've probably seen AND, OR, and NOT logic gates before, but if not, there are these little symbols right here. Now we can take their possible inputs and their outputs and map them on little tables called truth tables. This way we can look up their inputs and map them directly to their outputs. For example, a 1 and a 0 in an AND gate is a 0, and a 1 and a 1 in an AND gate is a 1. In order to produce a 1 and an AND gate, both inputs need to be high. On an OR gate, only one input needs to be high, or both. And on a NOT gate, it's just a simple inversion of the input to the output. Now, if you haven't used these directly or seen them, you've probably used them in a programming language like C or C++, where the logical AND expression is ampersand, ampersand, and the logical OR is pipe, pipe, and the NOT is just an exclamation point before a variable, a function return, or some other expression. In Python, it works a little bit differently, as these are reserved keywords as AND, OR, and NOT. If you read this in literature specifically related to mathematics, you probably see these symbols. And I remember these symbols by thinking of two hands coming down for an AND, grabbing multiple objects, or in an OR, the edge of a knife blade slicing one object in two so I can select one or the other. For the NOT, I like to think of a hockey player or hockey goalie sliding across the goal crease, denying a goal. In this case, he's not allowing the goal. But you can think of it any way you want. Now, the AND is known as a conjunction, the OR a disjunction, and the NOT a negation. Remember those terms because they're going to be important later. Now, what we can end up doing is taking these individual gates and chaining them together in a more complex logical circuit. In this case, the expression of this logical circuit is this equation here, which looks like this in Python, or this if you were to write it out in mathematical terms. If we condense all this down to the right-hand side of the screen to make room for this larger truth table, we can fill out all of the outputs based on those inputs. Since there are three inputs to this specific logic circuit, A, B, and C, we have two states per input, so we have 2 to the third possible states, or 8 possible states of like combinations going into this. So those are 0, 0, 0, 0, 1, all the way down to 1, 1, 1. If we take A, B, and C and assign them with their truth table side inputs on the left side, we can follow them through the logic gates to finally come to the output. In this case, a 0 and a 0 on an AND maps to a 0, and a 0 and a 0 on an OR maps to a 0, which is finally inverted to a 1. And we can slap that into the output on our truth table. We can solve for the rest of these outputs using Python in minimal effort by essentially taking the Boolean equation for this logic circuit with the 3 inputs and returning the output value. Now, why don't you give it a shot with something a little bit more complex? If you want, you can pause the video and try to work through this yourself. First, you should probably come up with an equation that matches this circuit. If not, you can actually try going to the truth tables, taking their inputs, and mapping them all the way through to the output. You don't have to do it if you want to, but we'll pause here for a second and I'll come back and we'll review it. Here's the resulting Boolean equation for this logic circuit. Let's walk through it and see how we got that. First of all, this piece comes from this AND gate, where B is diverted around the NOT gate into one input and then flows through the NOT gate into another, giving us B and not B. This piece comes from this OR gate, where A flows into one of the inputs of the OR gate, and the result of the bottom B and not B flows into the other input. We can take this piece, which is just the output of the bottom left AND gate that flows through the NOT gate over here. Finally, we take all of that and push it through the last OR gate, giving us the actual Boolean equation for this logic circuit. Getting back to SAT, it turns out that most SAT solvers take their input in a form known as conjunctive normal form. There's a couple of other forms too, like disjunctive normal form and negation normal form. The reason why most SAT solvers take their input as conjunctive normal form is because for an arbitrary Boolean formula, there's an equivalent CNF form of polynomial size. It means that we can take a formula, condense it down into a form that's easier to solve, that's still in a reasonable size. There is no such quality for DNF or NNF. This means that CNF is going to be the form that we attempt to take our arbitrary Boolean formula and crunch it down into a form to present to our SAT solver. This particular decomposition of arithmetic operations into stat instances is called flattening, or sometimes called bit blasting. There are eager and lazy methods to doing this, and it's a research topic in all of its own. In this particular case, the CNF form is what we want to focus on. SAT solvers are extremely powerful, but that power comes at a cost. Most of the problems that we have in computer science that we want to use SAT solvers for are not easily represented in a form that is acceptable for a SAT solver. Typically, what we need to do is express those problems, those constraints, those questions in a higher level form or language that can then be condensed down into CNF and then fed into a SAT solver that can use all of its theories to reason about these problems and solve them effectively. The types of problems that SAT solvers typically try to solve are generally NP complete, meaning that there's no good way to sort of generally solve the problem. We need to sort of make assumptions and guesses, which means that we're sort of intelligently brute forcing the problems that are posed to SAT solvers. These particular strategies and underlying theories that are used by the SAT solver is really important to the speed and possibility of solving specific constraints and problems. These front ends are called Satisfiability Modulo theory solvers, or SMT solvers. SMT solvers are sort of the front end or wrapper around SAT solvers or SAT solvers that give us control and allow us to express the problems that we have in a way that SAT solvers can understand. Let's see this earlier example where we had 3 logic gates into this logic circuit. We used this Boolean expression, which was easy to solve. In fact, the satisfiable inputs for this are 0, 0, 0, 0, 1, 0, and 1, 0, 0. This is easy to solve even with pen and paper. Now, in general, these particular problems are hard to solve. Here's a problem that is in conjunctive normal form. There's 3 clauses, and each clause has 3 literals in it. Now, we've represented this in conjunctive normal form, which means that the clauses are joined with conjunctions or ands. Each individual literal inside of those conjunctions are formed with disjunctions. This particular representation is known as 3-SAT. And while 3-SAT is a way that we can condense a problem down into a form that's suitable for a SAT solver, 3-SAT problems are NP complete. So this means that a SAT solver is going to have to try to use very clever strategies to solve the problem in a realistic amount of time. These strategies are called theories for the SAT solver, and it's going to be able to select which ones based on the constraints and types that you choose to represent your problems. These can be theories based on Booleans, bit vectors, arithmetic, and recursive data types. So SMT solvers are in fact extensions of SAT solvers, where an SMT solver will call out to SAT solvers using one or more theories and have them solve specific problems for us. There's lots of great SAT solvers out there, like WalkSat, Sado, Grasp, Chaff, ZChaff, Siege, and MiniSat. You'll see these referenced a lot in literature, and they've made great advances into the state of SAT solving. There's also a lot of really good SMT solvers out there, but 2 stand out in most of the literature, and that's Microsoft Z3 and SRI International's YICES. So if you want to learn more about specific SMT solvers and SAT solvers, there's an international Satisfiability Modulo theories competition, and you can go to this website to find out more about yearly competitions, benchmarks, and results, where researchers pit their SMT solvers against each other to find out which ones are solving benchmarks faster than others. So Microsoft Z3 takes its input in something called SMT lib format. This is sort of Lisp-like, and you can read more about it at the University of Iowa's website here. The problem is this isn't very intuitive. Although you can learn it, it's probably better to use Microsoft Z3's Python API. In this particular case, we can use the Python expressions and syntax that we know and love to solve specific problems much easier. In this particular case, let's take this inequality and solve it with Z3. We'll import from Z3 star. We'll ask for ints that are labeled as x and y for the solver. The variables are also x and y. We'll instantiate a solver class. And that particular solver will use the add method to add a specific constraint to the solver state. In this particular state, the constraint is the entire inequality that we want to represent. Note that we only use x and y variables which have already been declared as ints from Z3. In this particular case, we can run s.check to verify whether or not this is sat. If it is sat, then we can call s.model, which will give us some inputs that make this inequality satisfiable. So in this particular case, we end up taking the x mod 4 plus 3 times y divided by 2 is greater than x minus y, and plug in 1 for x and 1 for y, and indeed 2.5 is greater than 0. So the SAT solver did its job by solving this inequality for us by giving us one satisfiable condition. We can have Z3 give us more satisfiable conditions. However, we have to add constraints that say we no longer want x to be 1 and y to be 1, and then we have to resolve. And we can continue doing this until we've exhausted all of our space and we finally run out and return unsat. In this particular case, we can do this by using while scheck equals sat. We can print the model and then add our constraints again using this or clause. We can basically say x is not going to equal whatever came back in our model as the x variable, and y is no longer going to equal whatever came back in the model as the y variable. This will continue producing outputs until it exhausts all of them, as we can see on the right here. Now let's give this system of equations a shot here. Is this something that you think that you can solve with Z3? If so, give it a shot and pause the video now. If not, we'll come back and see how we can do this. All right, so in exercise 2.py, we've defined 3 different constraints to solve this particular question. What we have are 3 integers, x, y, and z, a solver state s, and then we literally just plug in our formulas as constraints into the solver. Then we check to see if it's satisfiable. If so, we ask for a model. Again, Z3 is going to return one specific model that satisfies all of this, not all of them unless we specifically ask it to. In this case, the only solution to this particular system of equations is z equals 123, y equals 173, and x equals negative 74. We can also simplify algebraic equations. For example, x plus 1 plus y plus x plus 1 is simply 2 plus 2x plus y. And that can be done with the simplify function in Z3. All right, so go ahead and give this a shot. See if you can simplify this with Z3. All right, so this is simplified with Z3 using this method. Essentially, it's the same exact thing, but since we only have one variable, we just use int instead of int to declare x as a variable. Then we pass the entire form into the simplify function, which will produce minus x or negative x to the 4th plus 20x plus 22 as our simplified form, which is correct. Keep in mind that in Python, 2 asterisks represent the power and the caret represents XOR. So just be careful with that. So we can also evaluate higher level functions, and now we're finally starting to get into the realm of what's interesting to us in security research and in computer science. So now we have this Adler32 simplified form here, in which we're going to take a buffer and the buffer length, and we're going to loop over that buffer and perform operations and return an unsigned 32-bit integer. This is the formula that we're going to try to model with Z3. Now, we have an application that will call that function based on command line arguments that are passed into this binary. It'll produce or generate the Adler32 checksum, print it out, and then check to see whether or not it's equivalent to 0D7502D8. This is the Adler32 checksum for lunch CTF with a capital L and capital CTF. In this particular case, there are lots of combinations of inputs that will produce the same checksum. Keep in mind that Adler32 is not a cryptographic hash, and collisions are perfectly acceptable. It's just a checksum. But if we want to try to solve for different inputs that satisfy this, it's actually quite easy with Z3. So here's the way that we model this particular Adler32 function in Z3. We have import from Z3. We're specifying a length, which is going to be the number of bytes in our input. This is the length of lunch CTF, which is what we use in our example. Next, we instantiate a solver instance. From here, we create an array, and in each component in that array is going to be a bit vector of 8 bits each. This is each bit or each byte inside of our input buffer. So each byte is going to be made up of bit 0, bit 1, bit 2, all the way to bit 7 for 8 bits per byte. We're then going to specify S1 and S2 as bit vector values of 1 and 0 respectively that are 32 bits each. Then for every byte or B inside of buffer, we're going to add constraints. Those constraints are essentially going to say that the search space for this particular problem is going to be within lowercase strings, A through Z, and uppercase strings, A through Z, uppercase. Then for the number N through length, we're going to go through and perform this particular operation, which is the same operation that's performed here in the Adler32 function. This for loop right here is simply represented as this for n in x range length. Here, there's one special thing going on in this 0 extension. If we look at the size of buff n, it's going to be 8. We need this to match the size of S1, which is 32. So we can 0 extend it by 24 bits, making it a total of 32 bits. We need to compare apples to apples. In this particular case, we can do the rest of this, which is just this particular operation. That operation comes from this location here. And then finally, we add our final constraint, and that constraint is that the output must equal this particular unsigned 32-bit integer. From here, we can take our S model, run a check on it to see if it's sat. If it is, we ask for the model. And then here we have to do some little funny business to take our bit vector and combine it into actual printable characters. And then we print that. If it's not satisfiable, we'll print unsat. So let's see how this works. What we're going to do is take the actual binary, which is example 4, and we're going to give it lunch CTF. This is going to produce a specific checksum. I can also mess it up a little bit, and the check will end up being invalid. If we want to run this solver, we can run example4.py. This will give us one input that it deems is satisfiable for this. So let's give it a shot. And indeed, the check is valid. That means that both lunch CTF and MZAVSDAA will both produce the Adler32 checksum of this value. What happens if we want to keep solving? Well, what we have to do here is we can actually get rid of this and then uncomment this guy here. This is essentially the same check for sat. We're going to ask for a model. We're going to combine this together into a string. We'll print that string. But once we're done with that, we need to go back into each byte within that buffer. Remember, our input buffer is going to be 8 bytes. We need to go to each one and say that the next buffer is not going to be equal to the current model's buffer on that particular byte. So we go through and specify all of this. That will essentially blacklist the last value. From there, we can say if it equals launch_ctf, we'll print a message and then we'll exit. Otherwise, this will continue going and going and going. So let's give this a shot. Here's our solving now. And if we let this run, it's going to run for a very long time. We should probably notice a couple of things here. One, all of the things that it's coming up with are 8 bytes. That's because we've specified that we want an 8-byte input. That's our bit vector length. And if we pause this at any point, we can spot check these. So we notice that they might look a little bit similar up to this point, but they're in fact different. They're all unique, and we can take any specific one of these and run them into our example, and it'll end up being valid. So this is solving and modeling a specific higher level function. There's a lot more things that we can do with SAT and SMT solvers, but the process is pretty much the same. It's extracting the information that you want to ask and representing it in a form that is going to be condensed down into CNF and presented to your solver. Solvers can be extremely fast, and sometimes there's really, really hard problems for them. Now, your solver doesn't just say whether or not it's sat or unsat, it's actually generating a proof for that satisfiability or unsatisfiability, which is another important component of SAT solvers. So I hope this has been helpful, and it's something that you can look forward to using on your next CTF or in work.